All right, today's lesson deals with compositions of transformations. That means doing more than one transformation. Sometimes you'll do, what are some of the beginning transformations we learned about? What was the first one we learned? Translation. Then we learned reflection. Then we learned rotation. What they're going to do for compositions is they're going to mix and match, and they're going to put multiple ones together. Sometimes they'll rotate a shape, then reflect it. Sometimes they'll reflect it and then translate it. So they can use any of these. Sometimes they'll translate, rotate, and they're putting together multiple transformations with a figure. So glide reflection is one that has a name. The other ones don't really have names. They'll just tell you to do one then the other. A glide reflection is first a translation and then a reflection in that order. Translation, then reflection. One more time, when you see that word composition, what should you be thinking? Composition of transformations. What's that mean again? A combination of more than one, of two or more transformations. So really, what is a composition? That's a composition right there. So one more time, if you have a shape like a triangle, sometimes they'll say translate it, and then maybe reflect it over this line. So you'll have your your A shape, your A prime shape, and then your B prime shape, double prime shape. Then you'll have B, B prime, and that's in the wrong spot. A double prime, B double prime, C double prime. So single prime. So that's what it could look like. So that would be a translation, then a reflection over something like the y-axis or the x-axis or the line y equals some number. Here's an example of what we've been talking about applied to a graph. Says the vertices of ABC are given. Find the image after a glide reflection. So the key thing you have to remember is, what is a glide reflection? Well, the glide means translate first, and then we're going to reflect. Oh, and it tells you that. Here's the translation and how to move it, and here's the reflection. So this is a very good problem to be able to do. I'll give you a second. Go ahead and graph triangle ABC. After you graph your shape, you then need to think about the translation first. So it gives you this notation. We can call it translation or transformation notation. So if this is translation notation, what does this part mean? X minus 8. What does that mean in English? It means left 8. And what does the Y, just plain old Y, mean? Stays the same. All right. So we're just moving left 8. That's pretty easy. You just count left 8 units, plot the shape. A common mistake is to forget to label the vertices. So make sure you label it. And also don't forget, if this is your new shape, they get the prime symbols, A prime, B prime, and C prime. After that, we can perform our reflection. And it says reflect over the x-axis. So I would highlight the x-axis to remember that's the line I'm going to reflect over. I'm going to reflect over the x-axis. Just want to remember that's where my line is. And we like reflections most of the time. They're usually pretty easy. So you figure out the distance from the point to the line. So this is 1 up. I need to go 1 down. There's my A double prime. The B prime is 1, 2, 3 units up from that line. I need to go 3 units down from that line. 1, 2, 3. There's my B double prime. Perform the same thing. That's 2 units away, and there's my C double prime. And there is our glide reflection. Down. So one thing we just discussed is if we were to change the order of these and do the reflection first, then the translation, here's where it would end up. We would reflect over and then translate. We would actually end up in the same spot. So that's pretty neat. A glide reflection is pretty special because you can go in either order and it'll still end up in the same final position. It would still end up over here in the third quadrant. The other thing we mentioned is a glide reflection an isometry? Well, if you don't remember, an isometry means it stays, the shape stays the same shape, same size. Yes, this would be an isometry. And how would you prove it? Since we don't have any 90s really, we would need to prove it with side, side, side. And how do you prove side, side, side congruence? So Pythagorean theorem, or distance formula, to prove the lengths of all the sides. So please keep that in mind. All right, example 2 is a little bit more challenging. First thing you need to do is graph that line segment CD, and then we'll be performing this reflection and rotation. So let's graph CD real quick. It's going to be -2 up 6. So there's that line segment. Up next, we need to do this reflection. It says reflect over or in the y-axis. It means the same thing. So here's my y-axis. I like to highlight it. So I'll do that in a different color. Here's my y-axis, and I'll note it so I'll remember that's the one I'm reflecting over. I want to reflect over the y-axis. So how do I do that again? I figure out how far each point is from that reflection line. So this is 1 unit away. There's my new D prime. This is 2 units away. There's my new C prime. There's my reflection, and that was pretty simple. Now to do the rotation 90 degrees, you need to remember when it doesn't say direction, we're going to assume counterclockwise. We're going to assume counterclockwise, so be careful on that. So what I'm going to do, since I can't really rotate my paper, I got to take a picture of it real quick. And now I can rotate this picture. So it said rotate 90 degrees. So that's what we do with our paper. We grab our paper and we rotate our paper 90 degrees counterclockwise. Once we get it rotated, we need to write down the coordinates of which of those shapes, my CD segment or my C prime D prime segment. We need to be dealing with the prime segment. So this is the one I'm going to focus on, and I'm going to write down its coordinates. And that'll be for C double prime and D double prime. So this is our origin, going left 1, 2, 3, 4, 5, 6. So that's -6 for my C, and up 2. For my D prime, it's pretty easy. I go left 3, up 1. So it's -3, +1. Now I can rotate my shape back, and I can graph these coordinates. So I'll graph them over here real quick. So -6, up 2. There's my C double prime. And then -3, up 1. There's my D double prime. And that's where my final composition will end up. Another thing we need to talk about is repeating reflections over parallel lines. So it's saying if we start off and have this segment called PQ, which is right here, and we want to reflect over line K. This line K is right here. If we want to reflect over, it's going to end up here. And there is my Q prime, P prime. But if we reflect over another parallel line, so K is parallel to M, it's going to end up back over here. What's another way that you could have ended up going from this shape to this shape at the end? You could have just done a translation. So the question is, how far would you have needed to translate? So that's what this theorem is talking about. This theorem wants you to think about how far you really needed to go to perform that translation. So here's the distance it's kind of talking about. From P to P double prime equals 2 times D. Well, what's this D? Well, that's this distance between the two parallel lines. So it's twice the distance between the two parallel lines. So once again, to go from P to this P double prime, it's twice the distance between these two parallel lines. You could say the same thing for Q. From Q over to Q prime, how far is that? Well, it's twice the distance from the parallel lines. The other important thing it wants you to see is that you have some perpendicular segments. So if you draw a segment from P to P double prime, it's going to be perpendicular to either one of those parallel lines. So it's just some key facts to be able to visualize. A lot of those are kind of common sense, but seeing them should help you a little bit. Let's look at example 3 to see what they're talking about. On this picture it says we have a diagram, and it has a reflection over line K and line M, kind of like what we just talked about. And so they want to eventually map GF to G prime F prime over to G double prime F double prime. And it gives us some measurements. It tells us FA is 6. So let's find that real quick. Regular F to A, that's right here, is 6. It also mentions that DF double prime is 3. So let's find that. D to F double prime, that's right here, is 3. Now it wants us to figure out some other pieces. It wants any congruent segments to each of these. So we're going to figure out which other segments are equal to GF, which other ones are the same as FA and GB. So I'll give you a second to write those down to see what you think. All right, so let's find the segments that are the same length as GF. So GF, let's find that real quick. G to F right here. You see any others that are the same length as GF? Well, you should have said G prime F prime, definitely. And G double prime F double prime. Those segments should all be the same because reflections will preserve isometry. Now we need to do the FA segments. F to A, that length right there. Do we have any others that are the same? Well, we have A to F prime. That'll be the same. Any others? GC and C to G prime. So I forgot, this is CG double prime and G prime C. Thank you. That one little prime is kind of hard to see up there, so be careful. So those are some quick examples. GB is the last little one, so we'd have B, G prime, F prime, D, and D double F prime. So those are some examples. The next little question we need to do is part B. And part B says, does AD equal BC? That's the big question. So those are over here. AD and BC, are those segments equal? What do you say? And this is yes. And it does say explain. Does anybody have a good explanation? So here's the key thing you should be able to say. We know these are perpendicular, therefore this distance is a nice little perpendicular segment to either one of these parallel lines. The question is, could we prove that these are also perpendicular, making these nice perpendicular segments? And the answer is yes, because a reflection will always reflect over that line. So this point will always reflect over that line perpendicular. So that will always be true. Therefore, BC is congruent to AD. So that's a good one. The last one says, what is the length from G to G double prime? I need to know that length. So let's go over and find it. So G is here. G double prime is here. And we learned a little trick a little while ago. It said, take whatever this distance is. We'll call that distance D. and do what with it? Double it. So the question is, how long is that distance? Well, if this is 6, this one is 6, and if this one's 3, this one's 3, and 6 plus 3 is, all right, so 6 plus 3 is 9. That distance D is 9. So that means the distance from G to G double prime will be 2 times D. 2 times 9 is 18 units. The last thing we're going to talk about is reflecting over some other lines, except this time they are not parallel lines. So it almost looks like a rotation here. So here we go. I'll read this time. I think it might help you. If lines K and M intersect at a point P, so here's K and here's M, and they intersect at a point P, then a reflection in line K followed by a reflection in line M is the same as a rotation about point P. So it's the same as rotating around point P, and you can kind of see that from that visual. The angle of rotation is 2 times x degrees, where x is the measure of the acute or right angle formed by K and M. So it's saying if you can figure out the angle between these two lines, and then you double it, that's the angle, total angle of reflection from A around to A prime. So here's what it's talking about. You have two lines that cross, and we'll say we have a point out here somewhere. We'll call it X, and we want it to reflect over, so it'll reflect over to here, and then it'll reflect over to here. How far is it from X to X double prime? Well, we'll say this angle is 30. If this angle is 30, what's the angle, total angle from X to X double prime? 60. You double it. So the total angle of rotation would be 60 degrees. We doubled 30 to get that value. So notice, this was a large reflection. I reflected a large distance away from the line, and this was a small reflection. So it's not always going to be the same distance when you're doing this type of problem. This matches up with example 4. It says in the diagram the figure is reflected in line K. So here's line K. There's P. There's an intersection with another line M. So it says describe a single transformation that maps F to F double prime. So here's F, and it's going around this way, go around this way, ends up over here at F double prime. We got to figure out that distance. What is that distance? Well, what is that angle of rotation? Well, here's the angle in between is 80. What did we do with it earlier? Yeah, we doubled it. So if we double that angle, so that's 80 times 2, we get 160. So we could have just said rotate 160 degrees. And if you say counter, I'd be happy. Rotate 160 degrees counterclockwise, and you'd end up in the same position as doing that those double reflections.